enough soon, but I did want to go ahead and continue to work through some problems having to do with the AP chemistry exam. So the question reads, the student is given the task of determining the iodide content of tablets that contain potassium iodide and an inert water-soluble sugar as a filler. A tablet is dissolved in 50 milliliters of distilled water, and an excess of 0.2 molar lead nitrate is added to the solution. A yellow precipitate forms, which is then filtered, washed, and dried. The data from the experiment are shown in the table above. So right here, you can see the data table as well as that question being presented. Well, we have to know how to write out the reaction. So it said that there was potassium iodide within the tablet. So I write out Ki for potassium iodide, and that interacted with lead nitrate, and that was aqueous. So I do have the phases of each of those compounds listed there. They then would undergo a double replacement reaction, and we would end up with potassium nitrate and lead iodide. Having to know our solubility rules, we know that lead and iodine are not soluble together, so they're going to form a solid compound there. So then in getting to the net ionic equations, I'm going to write down everything in its ionic form, except for those that are in solid form, which was our lead iodide. So for here, I have my potassium, iodine, lead, and nitrate. That's where we're starting, right? All of these in aqueous solution. However, in products, we end up with just potassium, nitrate, and the solid lead iodide. When I go to figure out the net ionic equation, I am going to cancel out the ions that are balanced on each side. So both of the potassiums get canceled, and both of these nitrate ions get canceled. I end up with just the lead iodine and my solid lead iodide for my net ionic equation for part 1 of this problem. The question B within this free response question then asks, explain why the reaction is best represented by a net ionic equation. And ionic equations are best represented because they show which of the ions are merely spectator ions and which of those actually react to form majority of the product. And in our reaction here, we can see that there's this even balance between the potassium ions on each side of the reaction as well as the nitrate ions on each side of the reaction. So those are going to be canceling out, and the excess being the lead. I have 1.698 grams, and that's for the mass of the filter paper and the product. So I'm going to subtract the mass of the filter paper, which is 1.462 grams. And after I subtract them, I have a mass of 0.236 grams. And that's for my lead iodide. So now I can use that as well as my molar mass number to go ahead and convert to moles. So I'll start with this 0.236 grams of lead iodide, and that will be converted into 1 mole of the lead iodide, and using my molar mass of my lead iodide as the conversion ratio. So to do this, I'll do 0.236 times 1 divided by the 461, and I will get 5.12 times 10 to the negative 4 moles of lead iodide. So that there is your conversion from mass to moles with the data that was given. And we have one more part to this question because of course okay. And for the last reaction, we were asked to find the mass percent of iodine that was in the potassium iodide tablet. To do that, we first start with the moles of lead iodide that we calculated in the reaction, which is 5.12 times 10 to the negative 4 moles of lead iodide. From there, I can do my mole to mole ratio between the moles of iodine in the compound of lead iodide compared to the overall mole of the compound. So I have 1 mole of lead iodide under 2 moles of iodine. When I calculate, I just take the 5.12 times 10 to the negative 4 and multiply it by 2 to get 1.02 times 10 to the negative 3. So I take that 1.02 times 10 to the negative 3 and I multiply that by the mass of iodine. And that's all over 1 mole of iodine. So I have a mass to mole ratio here. Once those numbers are multiplied together, I realize I have 0.130 grams of iodine inside of 1 tablet. So that is the mass of iodine in 1 tablet of the potassium iodide. So now that I know that, I can figure out the mass percent. So the 0.130 grams of iodine divided by the 0.425 grams, that is the total mass of the potassium iodide tablet. So this is grams of the, potassium iodide tablet. And I get 0.306, multiply that by 100 to make it a percent, and we end up with 30.6% of iodine per potassium iodide tablet. So that is the multiple steps to solving this particular free response question in